Yes.
I hate that now.
I have to decline that twice.
Yeah.
That's been saved to my documents.
Yeah, I think I found a way to disable OneDrive on this thing because it's never asked me for it other than when I open it up. I was just like, I'll never use Microsoft's OneDrive.
Okay, so I wanted to, are going to have, we're going to be non-zero. Right.
The shear components that contain the z-axis.
Shear components that contain the z-axis, right? So it's only going to be 3, 1 and 3, 2, right? Right? Those are the only components that are going to be non-zero, right? And the values, oh, I made my epsilons backwards. Right, so the only right, so we have a form that looks like this. So the strain depends on the absolute position, x2 and x1, right? But decays with the square of the distance, right? So at large distances, the strain goes to 0, right? And then at short distances, it becomes undefined, right? So that in the middle there, where it's undefined, causes a problem when we want to calculate energies, right? Because if we want to calculate energies, well, before we do that, how do we jump to the stress, right? Going from our strain to our stress should be pretty trivial, provided we assume that it's anisotropic. I mean, that it's isotropic, right? Oh, I missed a sign. Oh, no, I didn't. This is plus. Sorry. It's correct in the notes. Right, this just, right, the only thing we need to do is put our shear modulus out front. Right? Oh, yeah, GB. Right? So that's the stress field around an edge dislocation. Right? Our screw. Did I say edge? Stress.
You haven't been saying edge. You've been saying screw.
Okay. This is around a screw dislocation. I was looking at the picture. The stress field around edge dislocation is quite a bit more complex because your displacement field depends on a lot more things, right? Your displacement field is going to depend on the width of your dislocation core, which is going to depend on the properties in the planes, right? So in order to get the stress field for an edge dislocation, you have to go a little deeper into classical elasticity theory and assume the most straightforward way is basically to think about in terms of the area stress function, and you can work it out. But that's a little too beyond the scope of, I think, what we need. So we just give the stress field for an edge without without commenting on it, right? But this stress field leads to something really important. If we consider that our strain energy density, right? Right. That's the mechanical energy of our dislocation. Right? Which, if we work this out, right? So this ratio here is R1 is how far out we integrate. R0, because we have an undefined strain at our core, we have to choose some point outside. Now there's other ways around it, but again, for the purposes of the class, what really matters, right? I think this is the most important thing from the entire dislocation lecture, is that the strain energy is going to be proportional to GB squared, right? The energy of a dislocation, right? And this this gives rise to splitting of partials is the example, right? This controls pile-up behavior and yield behavior in lots of ways, right? So when I'm thinking about materials problems, right, in mechanical sense or just in general, I have a set of rules of thumb, right, that are my go-to ways to start thinking about a problem, even if I'm not familiar with it, right? If it's diffusion, if it's thermal, right, I immediately think Arrhenius, right? All right, if there's anything with temperature dependence. If it's diffusion, it's square root dt, right? If it's dislocations, it's GB squared, right? If it has anything to do with solubilities or alloying or phase separation, it's the Hume-Rothery rules, right? And these are kind of my basic toolbox of how you can start to think about, even if you don't know anything about the system, right? Make some educated guesses about what the heck is going on. And GB squared is the most important thing to remember, right? About dislocations, right? And it controls so much of the behavior, right? Immediately, we see why the dislocations that we see in most systems tend to be on the close packed planes, right? With Berger's vectors along the close packed directions, right? Shortest Berger's vector, right? Why twinning in hexagonal metals is so much in some cases is so much easier than prismatic slip, because the twinning dislocations have a much smaller Berger's vector than C plus A dislocations in these systems, right? So we haven't talked about these things yet, but this is going to keep coming up over and over and over again. GB squared. Oh, the other important rule of thumb, whenever it's polymers or glasses, free volume, right, is my go-to my go-to starting point. Okay. So then I wanted to work through right, an example of so the Koehler. Right, so I want it to go through the simplest example that I can. Except let me reorder my axes here. All right, so what I want is a screw dislocation that's lying on the z-axis. And then another screw dislocation that's parallel to this lying in the x1, x3 plane. Right? So both of them are in the x2 equals 0. x2 equals 0 plane. Right? And what I want to know is...
Sorry. Wait, where's S1 lying again?
S1 is lying on the z-axis, the x3 axis.
Okay.
Right? X... Yeah.
Okay, so it's coming... Sort of.
Yeah, it's coming...
Okay.
Right, so this is Z, 1, 2, 3, right? So I just want to make sure I had a right-hand system there. Right, and so the other, I think, there's a couple things like line tension is going to come up in strengthening. So we're going to do a lot of things with that. But I think the other real important kind of pure dislocation thing is interactions, right, between dislocations, and understanding what this is the fundamental, what's fundamentally behind all the dislocation dynamics codes, right? I have a bunch of dislocations in my system, and they're going to move based on the external load that I apply and the interactions that come up between all the dislocations. Right, so what I want to know is in this case, right, the force on S2 due to the presence of dislocation S1. Right. So what we can do we can write this in terms of an angle and a radius, right? Just setting our coordinate system, right? This will be a little bit more convenient than x and y, right? Because our force, right? We have a symmetry in our system here, right? Right, at the end of the day, it should only depend on we'll get to there. I'm jumping ahead. Okay, so why is S1 exert a force on S2? There's a stress field, right? Okay, what direction does the force act on S2?
Are these screw dislocations?
They're parallel screw dislocations here. So the Burger's vector is arbitrary. We're not going to say which. Right? We know it's we know that it's either they can either have parallel Burger's vectors or anti-parallel Burger's vectors. Right. So what direction?
The repulsive.
It's going to be repulsive, but I meant in a more general case. Right. It can either be the force can either be attractive or repulsive. Right. But which direction is it going to be acting in? Right. Or which? Not direct. If you ignore the sense of the vector, where is that? Which? Right. So
Perpendicular to the Burger's vector?
yeah. So it has to be perpendicular. Right. The force is always perpendicular to the dislocation line. Right. In this case, it's either going to be in the plane in an attractive sense or a repulsive sense. All right. Okay. So what's our relationship? What's our force? What's our expression for our Koehler? So this should have been, you should have seen this in defects, right? You had to have done some calculations with it, I'm sure.
Yeah, we did.
Oh, yeah.
Right. So I'm just reviewing some of the most important ones. Right now, unfortunately, again, it depends what reference you look at. Right. T is the, in this case, T is, well, I'll just be consistent. There we go. It's the tangent to the dislocation line. Right. So sigma dot B, right, this is sometimes called the G vector. Right. So different authors put the cross product in different directions. What's that? Yeah, so what it does is it gives you the opposite sense of the force, right? So you just have to be careful about how the reference that you're reading defines your conventions, right? Which way you're going around your Burger circuit, right, defines which way your Burger's vector points, right? So you just have to check the convention and be consistent all the way through, right? As to whether you're thinking of Burger's circuits that go clockwise or anti-clockwise.
I have a question here.
Yeah.
So sigma is it's not the scalar. It's our stress tensor.
It's the
right?
stress tensor.
Stress tensor, and that's the dot of B.
Yes. So we're going to talk about the physical meaning of this in just 1 second, right? So. Right. So sigma dot B. Right. What does this actually mean? Right. So sigma dotted with a unit vector
It gives us scalar.
gives you
It gives us a
it's going to be a vector, right? So sigma n, right? This is attraction,
yeah.
right? So what this is this gives us the force on a plane that's perpendicular to the normal vector. Right? So what this gives us, this is related to attraction, right? This is the force acting on a plane that is the perpendicular to the Burgers vector, scaled by the Burgers vector. Right? Because B is not a unit. B is not a unit vector. Right? So this gives us a resolved force. Right? Now what does the cross product then give us? Right? So now I'm doing a cross product times a cross product with a force, and then I've got a L, which is a tangent vector. So that's a normal, right? So what's the physical meaning of that? Right? So if this is G, right? Right. Where else in physics do cross products pop up? Okay, so in a torque, right? So what does torque? What's torque? Yeah, right. Right. This is basically a moment. Right. Right. This is the unit vector that tells us the direction. Right. This is a force, and so what direction is the force? This is the resolved force due to the stress. So what is now our the direction of the force on our dislocation has to be perpendicular to L.
Just like in R cross L, it's perpendicular.
Yeah,
So L is just to make sure
it's the tangent line
tangent.
to the dislocation. Right? So again, right, it's consistent with our understandings. The force has to act perpendicular to the dislocation line. Right? Okay, so let's go back to our problem real fast. Right? So our stress field around our first screw dislocation. Right? So 0, 0, G, B, Y, 2 pi x squared plus y squared, 0, 0, minus GB x, and this might be opposite. This is opposite in sign to what I showed earlier. And again, that's the convention. Right, where the reference where I went through this work happened to use a opposite convention than what. I wish mechanics people would get act together.
Organize a conference.
It's a little more than that.
If you make it a nice spot,
All right, so let's just write this in terms of polar coordinates. All right. Okay, so that's just the stress in polar coordinates, right? So of course x is equal to r sine theta, and y is equal to x is r cos theta, sorry. Right, that's just the conversion to and from polar coordinates. Okay. Okay, so if we go back to this equation, sigma dot b cross L. Okay. Is this the Burgers vector for S2 or S1?
S2, the one that is
S2.
being acted on.
And this L, this is also S2. And this is the stress field from S1. Right? So we want to keep which terms belong to which dislocations, right? So this is basically the force acting on the plane of the Burgers vector, right? The plane defined by the Burgers vector for S2. Okay, so the Burgers vector for S2 acts in the z direction. Right? And so in this case, right, we just take G, the dot product of our sigma dot b, right? This is really straightforward. This just gives us the vector. Let's keep G. There we are. G B S1 sine theta B S2. Right. Right, so now we've got a vector that looks like that, right? That's just matrix multiplication, right? And then our L vector for S2 is nothing but this, right? And so sorry.
We have the video.
Yeah. Right, so we can write this in indicial notation. L. I keep wanting to use T for tangent. Right? So in indicial notation we have this. Right? So epsilon I 3K L 3GK, right? All the others are zeros. Right? And then we only have two terms that survive out of this. Epsilon I 3 1. Oops. L 3G1 plus epsilon I 3 2 L 3. Right. And then obviously this, obviously I has to be 2 here, right? Otherwise that doesn't survive. And it has to be 1 here. So this is a negative permutation. This is a positive permutation. All right. So terms that survive, we have 1. Or we can write that in terms of polar coordinates as all right, and that's the BS1, BS2. Okay, right, and so that's our force, our interaction force between the 2 dislocations, right? And so what we see right away is that if these are parallel, right, we're going to have a positive force and they're going to repel. And if they're of opposite sign, then they're going to attract, right? Which makes sense. But this is just work through it. They all follow basically the exact same. All the problems you can set up are the exact same process. The trick is I need to write my stress field and my line direction and my Berger's vector in a form that we can multiply things out, right? So when it's easy, it's straightforward enough when you have a set geometry, right? When I say I want 2 parallel screw dislocations that lie in the same plane, right? But what about a screw that's at an oblique angle with an edge where they're not going in the same plane, right? Writing them in a general, solving the equations in a general sense can be a pain right in the rear, right? Because it's easy to do numerically, but to generate an expression in terms of position along the line and angle between the lines is tricky, right? But if I know what the distance is and I know what the Berger's vector is, then numerically doing it is easy. So, okay, so we'll stop there and we'll answer that other question on Monday. We'll take homework questions on the dislocations and make sure you watch the videos, the lectures before.